Hi, today we will talk about stability support by power-to-gas conversion. Specifically, we will explain the role of power-to-gas conversion in a subdomain of power-to-gas flexibility in multi-carrier grid integration. Including here, we will elaborate on the system or components needed for such integration. And then finally, we will identify several strategies for the control of electrolyzers in the stabilization of electrical power systems. Let's take a real-world example of a power-to-gas system located in the Netherlands. In this figure, we see a high deployment of renewables, primarily with farms in the North Sea, and a cluster of systems and equipment for the production of hydrogen gas. Here we notice that the renewable energy is the main type of power source in facilitating the process of power-to-gas conversion, so that hydrogen gas is produced from water. This conversion is mainly done by a device called an electrolyzer. Electrolyzers can be connected to the power system by the help of power electronics. They can adjust their demand, while at the same time they can react very fast, for instance in a time frame of several milliseconds. Thus, they can support the system with fast control actions to help stabilizing the power grid, such as stabilizing the active power balance. If the electrical power system experiences fluctuations or power imbalances, stability phenomena is excited, and without effective control, undesirable cascading outages, power disruptions, or even blackouts can occur. As illustrated in the figure, if a large renewable energy-based power plant suddenly disconnects from the system, very fast control actions are needed to prevent steep and large frequency deviations due to an imbalance of active power. We can use electrolyzers to perform such control actions, which is more effective than existing solutions used in conventional systems. Now that we have understood the importance of power-to-gas conversion for the stabilization of electrical power systems, it is time to discuss about the necessary models and strategies needed for stability support by electrolyzers. The first one is about building a dynamic electrolyzer model, and the second one is about identifying special active power regulation strategies of FAPR, which can be then used by an electrolyzer or, in general terms, any controllable element belonging to a renewable energy hub, which can comprise an electrolyzer, a battery storage, and/or a renewable power plant. For the electrolyzer model, a schematic of different components are shown in the figure. This model does not only contain the electrical parts, but also includes power electronic converters and other auxiliary systems. Also, a connection to ancillary components are depicted in the schematic. From this model, we can then build the necessary representations on top of it for a simulation and the analysis of power system stability. The usual practice is to connect such a model to AC systems using an AC-DC converter. On the other hand, electrolyzers also have DC-DC converters that are used to regulate the amount of current that is needed for the production of hydrogen. Now, let's proceed to the fast active power regulation. Special fast active power regulation strategies are essential to enable stability support by electrolyzers. The main goal of implementing fast active power regulation is to mitigate unacceptable frequency excursions from the desired nominal frequency value. A fast active power regulation strategy acts within the so-called frequency containment period, which occur in a time frame of milliseconds to several seconds. Additionally, electrolyzers can contribute to subsequent periods, like manual or automatic restoration towards the nominal frequency range. In principle, different fast active power regulation strategies can be used. For example, the so-called droop control can be adopted for as fast-active power regulation. The droop fast-active power regulation is in line with the typical strategy used in conventional power plants and power electronic interface devices. This technique senses the deviation of frequency and proportionally adjusts the active power reference following a certain linear or slope characteristic. Another strategy for fast-active power regulation can be defined to perform in a combined droop derivative fast-active power regulation. This strategy is composed of two loops, where the first one performs a proportional control action, and the second parallel loop, called the derivative loop, takes into account the frequency derivative, which senses the rate of change of frequency, and then performs a fast adjustment of active power by using a washout filter and a gain. In this way, the combined droop derivative fast active power regulation adjusts the active power consumption of the electrolyzer that attempts to prevent a steep rate of change of frequency and a large frequency deviation. The last method for fast active power regulation is the virtual synchronous power, or VSP fast active power regulation, which uses a second-order transfer function to quickly adjust the active power consumption of the electrolyzer to mitigate steep rate of change of frequency and large frequency deviations. The VSP-based fast active power regulation also allows electrolyzers to contribute in damping out frequency swings. As a real-world example, the previously described control strategies were applied to a 300 megawatt electrolyzer plant, of which its integration was studied based on synthetic systems representing a futuristic situation in the north of the Netherlands. As shown in the figures, electrolyzers can quickly and effectively adjust their active power response by mitigating both the rate of change of frequency and the maximum frequency deviation. Such performance is prominent in advanced strategies like the combined droop derivative or the virtual synchronous power are attached to electrolyzers. In summary, the synergy between the electrical system and gas systems such as hydrogen unlocks potential for new control principles to safeguard operational flexibility of the electrical system. Electrolyzers' demand-side response can significantly enhance the dynamic performance, a timescale of milliseconds, of the electrical system, which increases its resiliency. Power rating, location, and optimal controller design are key parameters for effective stability support for electrolyzers. New control principles for stabilization of low inertia, chaotic systems like renewable energy hubs should be urgently developed to accelerate the energy transition.